All right, well, good afternoon, everyone. My name is Rachel Gare, and I'm at Purdue University getting my PhD under Dr. Linda Lee, looking at some PFAS remediation. And so diving right into it, since I just have 5 minutes here, we know that one of the successful methods of PFAS treatment has been reductive transformation of these compounds. And several zero-valent metals, particularly zero-valent iron, is a really strong reductant, and it's also pretty inexpensive, so it's pretty accessible. But it is easily oxidized, which calls for the addition of a catalyst. So we also know that since nickel is stable in several valence states and it's also an inexpensive metal, this would work great for working alongside the iron. So one of my former lab group members, who is actually Jenny, who's presenting after me, she began synthesizing nanoparticles in the lab with zero-valent iron and nickel. And since these particles could clump together, activated carbon was mixed into the solution to disperse the particles over a larger volume. And as seen on the graph on the right here, PFAS experienced reductive transformation close to 60% within the first 24 hours of the reaction with these particles. And since this process was so effective, my task now is to look at how to make this process more efficient and also make it implementable in the field is really our main goal here. So we want to scale up the process so that this can be used on industrial and military sites. Currently, synthesizing the particles takes about 8 hours and it produces about 25 grams of the particles, which is a pretty low amount. So some of the key questions that I've been asking is addressing each of these steps to see if some of them can be removed or perhaps condensed to make the process more efficient. So just a quick overview of the synthesis process. We have a really specific method for how we add the iron, our granular activated carbon, and the sodium borohydride. We then wash the particles 3 times with DI water, which is a pretty intensive process that consists of using a centrifuge and taking off the supernatant and adding more DI water, so it's pretty time intensive. We then add our nickel chloride and then stir for 3 hours. And so we want to look at maybe if we can reduce that stirring time as well. And then the particles are washed 2 additional times before they're finally ready to react with PFAS. So since washing the particles is so time intensive, we want to see if we can reduce that number of washes. Or perhaps if in those first initial steps there, maybe we can add nickel and iron at the same time rather than separating them with the washing process and see if the particles will still be reactive. But perhaps the most important question here is how can these particles be stored over time? So rather than synthesizing them and using them immediately for field applications, can they be stored, whether it be dry or wet, perhaps solvent rinsed, and will they retain their reactivity? And then how long after they're stored are they still reactive? So some of the current results we have show that particles that were stored just wet, they were just, all of the excess water was vacuumed off of them, but they were still fairly damp. They were stored for 7 days and they were no longer reactive. We saw no PFAS destruction with those. We've also tried using a methanol wash instead of DI water, and that just killed the reactivity. We saw no reaction when that happened. And I also tried adding nickel without washing out the excess sodium borohydride, and that also reduced the reactivity. So far, the methods that we've looked at have not been the most effective. And so we want to continue working on really making this process the most effective it can be. So for our future work, we're looking to increase the particle production efficiency. And again, we want to lower that time of 8 hours down to as little as possible. We want to determine a reliable storage method that does not decrease the reactivity. Some of my upcoming experiments will look at introducing spectroscopy into the process to look at the valence states of nickel and iron during each step of the synthesis, as well as during the reactivity with PFAS to see exactly what's happening throughout the process. And we continue want to look at decreasing the washes as well. So we're going to use spectroscopy after each wash to see if there's a difference, and if we can decrease the number of washes. And finally, again, we've tried storing the particles in different solvents or with the dry storage to determine the shelf life of these particles. And so we want to continue some of those experiments. We have a couple ideas of some other methods of storage that might be more effective and will perhaps even improve that reactivity with PFAS. And so once we have some answers to some of these questions, we have some plans to get out to the field and actually conduct some field experiments to see if these can be effective with a groundwater matrix. And that's all I have today. So thank you for your time.